Hello, this is a demo of problem 1 and problem 2 in your assignment this week. Both the problems are really similar, so you shouldn't have any difficulty following this demo for either problem. You're allowed to do this by hand if you want to. I will demonstrate in Excel for the sake of it being easier. There are some old demos in both ways here if you want to look at them. So in this demo, you're asked to use the 0.01 significance level to test the hypothesis that corn plants grown in untilled soil will have less pest damage than corn plants in general. A sample of corn crops grown in untilled soil experienced mean pest damage of 10.2. The average mean for the population was 15.2, with sigma of 4.1 normally distributed. So let's go ahead and parse out this problem. Population 1, our research by population, H1, corn plants grown in untilled soil. And population 2, H0, corn plants in general. Our dependent variable, what we're measuring is pest damage. And the tails of our distribution are, we see that word less, so one tail low. Our research hypothesis, I want you to start getting used to writing the shorthand. So for the shorthand, we would just write mu1 is less than mu2. And in longhand, we would write it all out and we would say population 1 will have less pest damage than population 2. And we can copy and paste this for the null hypothesis, just replacing the less than sign with an equal sign, and we'll add this word not here, will not have less pest damage than population 2. The center of the comparison distribution, based on the central limit theorem, we know that the mu for the distribution of means is the same as the given mu, and that is 15.2, shown up here in the problem. And the spread, we know we have to do some calculating. I see I have this all written in here, so I'm going to just get rid of it so that we can solve it fresh. We have to calculate the spread by using the spread for the distribution of means. And in this class, we use all 3 steps to solve that problem. So I'm just going to zoom out a minute and I'll write those down because I know these are new this week. And so we have, we start with sigma, then we calculate variance, which is the same as sigma squared. Then we calculate the variance for the distribution of means. Your book writes this as sigma squared for the distribution of means. And all it is variance divided by n. Again, you'll see this in places written as n minus 1. We're not there yet. This is the formula we're using. And then we have the standard error, which is the same as sigma for the distribution of means, equals the square root of the variance for the distribution of means. So those are the formulas we'll be using. Let's pull some information out of the problem. N, I can see a sample of 26 corn crops. Let's write 26. Mean for that sample was 10.2. I'm just pulling this right out of the problem. Here it is. We have to calculate Z. We're not ready for these yet. Let's go to mu, which is 15.2. And sigma given is 4.1. And so let's go ahead and calculate variance equals sigma squared. Let's calculate the variance for the distribution of means, sigma squared divided by n. There is a slower demo of this linked up here if that's helpful to you. And sigma for the distribution of means, or SE, is the square root of varm. So we have the standard deviation for the distribution of means is 0.80, etc. So let's go ahead and write that. SE equals 0.8041. We'll do 4 decimal places because we need to calculate it with the further. The shape is normal, and it's the distribution of means. You don't have to write all this out, but I think it's important to keep these straight. For n equals 26, because remember that distribution of means will look different for each sample size. Next, we find and plot the cutoff point. Let's see if it's stated. It says we'll use alpha 0.01. And the cutoff point for associated with that, we can use our critical value calculator tool, which we'll use this one now. Scrolling down, we see that this is at 0.05. We'll change it to 0.01. And actually, this is the T calculator. So let me get up our Z-score calculator. This is the one that you'll be using, Z critical value calculator. Alpha is set to 0.05, and we don't have to tell it anything about our N because these don't change. We can see that for let's see if I can get that out of the way so we can see. We can see that for that test, we need 0.01 because that's what was stipulated. I don't know how I can get this out of the way, so seems pretty stuck there. Let's change that to 0.01, calculate, and going down, we find that the critical value for a one-tailed test is 2.33. We're doing a one-tailed low test, and so it's going to be minus 2.33. Z alpha is minus 2.33. You see this in some places written as 2.32. Don't worry about that. We'll make the best of that because it's kind of in the middle here. So here's our critical value. Z alpha is minus 2.33. Let's get our highlighter and shade the tail. As you know, if you don't have these tools, there are a couple of ways you can do it. I happen to have a pen. I teach, so it's really important for me to have it. If you're having trouble, just click in a cell. I'm going to go this route with my pen. I'm using my pen, but you can also draw with your cursor if you want to, or you can insert shapes. So whatever works for you. So here is our, this is all related to the null hypothesis. This is related to population 2, and we know that the fail to reject region, the non-significant region, come on, pen. The fail to reject HO, failure always means NS non-significant, is all of the space in the center here, and this shaded region is the reject HO region. This is the happy region. Researchers like rejection because this is significant. All right, continuing on, we calculate Z sample. The formula for Z sample is just sample minus population mean divided by spread. In this case, our sample is M minus our population mean is mu, and we're dividing by whatever the spread is. In this case, our spread is SE, or sigma M. And so let's go ahead and solve that formula. Equals, to do a formula, parentheses, sample mu minus population, sample mean minus population mu divided by sigma M. And when we do that, we find we have, wow, a really significant effect from here. We can see that our sample score is so far into the tail that we don't even have room to plot it. So let's go ahead and just get our pen here, and let's just indicate that our sample score is really far that way. Z sample equals minus 6.22, very, very significant. ZS equals minus 6.22. We can't even fit it on here, so this really made a big difference to our corn crops in this study. This does allow us, because it's in the shaded region, to reject Ch05A and state our hypothesis. We can just grab the text from up here and fill in the blanks and make sure it makes sense. So here's the basic statement. We know population 1 are these corn plants grown in untilled soil. We know it's not have because we've done the test now. Have less pest damage than corn plants in general. And we always have to state the concluding statement. We tell what test it is. We did a z-test. Now that we have more than one, we have to tell the number in the sample. In this case, we had 26 corn plants. And so we write it in parentheses after the z. Then we put our equal sign and we write the sample z-score, not the cutoff point, 6.22. And then it is significant, so we have to tell the p-value we tested at. P is less than 0.01 is what we tested at. So we have a significant result. The last thing we do is we want to state our confidence intervals. And to do that, all we need to do is we need to figure out what the cutoff points were for a two-tailed test. So the 95% confidence interval, we have to look off the cutoff points for a two-tailed test at 0.05. And so, did I lose my calculator tool? Here it is. We can already see that if we change alpha to 0.01, we change it back to 0.05 and calculate, we can see that this plus minus 1.96 are the numbers that we need to use. So let's go ahead and just put these, let's see. The 0.05 cutoff, I'm just going to write it in here, 1.96. And let me get the other one right away too, the 0.01 cutoff. It's the very same thing. We use the very same tool, except we change it to 0.01 and we look for the two-tailed test. In this case, it's 2.58. And so let's go ahead and put that in here by the 0.01 cutoff, 2.58. So in a nutshell, what we're doing is we're figuring out the raw scores associated with these two z-scores, and we're plotting them right around the sample mean. So what we're determining is, does this distribution for the sample mean include the population mean? And so let's go ahead and use these formula. The lower cutoff, let's use Z, or the lower CI. I'm going to change that to CI here. I better do it appropriately so I don't have a bad example in here. The lower range of the confidence interval equals, let me get this right too. We're going to take that 1 point, and we're looking at 95%. We're going to take that cutoff point of 1.96 and put a minus sign in front of it. So that's this 5% cutoff. We're going to multiply it by the standard error, 0.8040. We're going to do this in Excel. And we're going to add to it the sample mean, the mean for the sample. Okay, so as we do this, I wrote out these numbers here. Let me write it out in a formula now. The lower CI for 95% equals the negative z-score associated with alpha times the standard error plus the mean. So let's go ahead and do that formula. The lower cutoff equals, in parentheses, negative 1.96 times standard error plus sample mean. And that's the same as the formula that you used earlier in the semester when we what it's telling me is I accidentally put an equal sign in there. So let me fix that right here and get the plus sign in there. That should be better. It's really tiny on my screen. That looks good. Okay, so then we have the low end of the confidence interval for 95% is 8.62. The high end is the very same formula without the negative sign. So the high confidence interval at 95% equals, same thing, ZA times standard error plus mean. And so we just do the very same formula. Equals parentheses, there's our 1.96 times our standard error plus our sample mean. And so we're getting 11.77. So our confidence interval is 8.62. So we'll write 95% confidence interval equals 8.62, rounding to 2 decimal places, to 11.78. Let's do the same for a 99% confidence interval. You can undoubtedly guess that the formula is exactly the same, except we're using the 99% cutoff right here. So let's go ahead and get our equal sign, parentheses. We're doing the lower end, so we'll put our minus sign, 2.58, times our sigma m, or SE. And then we're going to add the mean. And so we get 8.12 for the lower end, or 8.13. The high end is the very same formula. We're going to get the 2.58 times the sigma m, or the SE, and add the mean. And that gives us a high end of 12.27. So the 99% confidence interval equals 8.13 to 12.27. So if we were going to color those in on the chart, we would have, we're not going to do that because it seemed like it's too messy, but we could say, interpreting this, that we are 95% certain that the population mean is somewhere between 8.62 and 11.78. Or we could say we're 99% certain that the population mean is somewhere between 8.23 and 12.27. And since our population mean of 15.2 doesn't fall in either of those ranges, we are really confident in our decision to reject the null hypothesis.